All right, hi Dane. We're here for our first video on atomic structure. So get your paper and pencils out and get ready to take some notes on some things too. So we're going to talk about the structure of atoms, and we're going to do a little historical part here in the beginning. Think about how the Greeks thought about atoms. So they were, great philosophers. But they were not good scientists. They just talked about stuff and theorized about things. So they thought that everything in the world was made of four elements, and those four elements were earth, water, air, and fire, in that order. So as we think about the elements. And one thing that they thought about was like a rock is a piece of earth. It would fall through the air and it would fall through the water and it would go to its natural position of being with the earth at the bottom. So, it's a okay idea, but it doesn't really hold up when we start investigating it. And like I said, they weren't scientists. They didn't test their ideas. They just talked about stuff, right? So the classic example is burning some wood. So they thought wood was made of earth and air and fire. And when you burned it, you released the fire out of the wood, and you also released air, which was the smoke, and then the ash was the earth part, and that came down to the bottom. So they did come up with an important idea of the atom, and it comes from the word atomos, which means undivisible. So when you think about something like bread, if you had a small piece of bread and you take that little piece of bread and then you break that little piece of bread up into a little tinier piece, and you keep breaking the little piece of bread up, and it's smaller and smaller and smaller, and then you get down, it's like, well, how far can I do that? How long can I keep dividing this little piece of bread and it still be bread? And they thought, well, is there an end limit to this? And most of them thought yes, and that end limit is the atom, is what they said. That's the undivisible part of it. So, again, not a bad idea, but not quite correct. What we know now, what they were thinking of as atoms, we would call molecules, where we have a compound like bread or like water, H2O. And we can break that down, break the piece of water apart and apart and apart and apart and apart and get down to a single molecule of water. We can break that down further, but then it's not water anymore. It's hydrogen and oxygen gas. And so that idea that there's this smallest piece of something, and that's where the idea of atoms comes about. Another important historical person is Dalton, and he had his theory of about matter and atoms and how it all comes together. So we'll talk about his theory, and then we'll come back to it later and talk about modern theory about it. So he said, first off, his first postulate was that all matter is composed of extremely small particles called atoms, which cannot be subdivided, created, or destroyed. He also said that atoms of a given element are identical in their physical and chemical properties. Atoms of different elements differ in their physical and chemical properties. That's what makes them different. Atoms of different elements combine in simple whole number ratios to form compounds like H2O. We don't see H 3.8, O 1.2 or something like that, right? It's in whole number ratios. And the last thing he said, that in chemical reactions, atoms are combined, separated, and rearranged, but never created, destroyed, or changed. Another important historical figure was Rutherford. He did an experiment with atoms, and he used a piece of gold leaf, which we saw in class, very thin leaf, and he was shooting these positively charged particles from a radioactive source, alpha particles. And let's see what they say about it. Oops, I'll turn the audio on here first. Hello, where's my mouse? There it is.
And Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So, going over this again, and when we think about Rutherford's experiment, and earlier, before Rutherford, there was a guy named J.J. Thomson, and he discovered the electrons, and he used a cool apparatus where he used a magnet and had a beam of electrons and got the beam to deflect and determined that they were negatively charged. But Rutherford, from Thomson's experiment, they thought, well, these electrons are just right around on the outside. It's easy for them to get knocked loose. And then Rutherford knew roughly the size of an atom, the volume, and he knew roughly the mass of an atom. And so, knowing the mass and the volume, he figured the density of the atom, and it wasn't that great. It's not that dense of stuff. And he thought, hey, I got these alpha particles, they're going really fast, and they'll just rip right through them and go to the other side. And the original part of his experiment was not like what we see here in this picture. He just had a screen on the other side of the foil, not a ring all the way around it. And he was expecting these things to rip right through this gushy atom stuff that wasn't that dense, and just maybe get deflected a little bit, curve off to the side a little bit or something. And so he set up a screen, and the alpha particles, when they hit the screen, they would illuminate it, light it up, kind of like a TV screen gets lit up by electrons. But as they go through and hit that screen, and he found that he knew the rate that the particles were coming out of the source. And then he was measuring them on the screen, and they didn't match up. He was missing some. So then he made his screen a little bit bigger, and then picked up a few more. And then eventually, after a while, he wrapped the whole thing around it, like you see here in the picture. And he was getting particles bouncing straight back almost. And this was super confusing to him, because they knew the atom's density, and they thought, well, it's not that dense of stuff. It should just rip right through it. And his analogy, he said, he was so surprised. It was like shooting an artillery shell, big giant bullet that that they shoot at planes and stuff from a big giant gun. Shooting an artillery shell into a piece of tissue paper and it bouncing back, because they did not expect this. So when they had the particles, colliding through, and you see that most of them are going straight through, there's a few that deflect over to the sides, and some deflecting back. So that was super surprising to them. And he's the one who came up with this idea that the atom is not uniformly distributing this mass evenly, that there's a small collection of mass. Oh my gosh. Do not do that. Oh my gosh. What is going on? Here we go. Okay, sorry. And there we go. That's what I want. When we think of the atom, and even this picture where they show the atom and they show the nucleus in the center, that is way out of proportion. If you think of that whole atom as like a football stadium, like the Seahawks stadium, and the nucleus would be like a golf ball on the 50-yard line. If we were flying this high above the stadium where you could see it, you wouldn't be able to see a golf ball. It'd be so small. So even this picture is out of proportion. So most of the atom is empty space, and that's how these particles were just flying right through, straight through. But every once in a while, something would come in contact with that nucleus and get bounced pretty much straight back. So Rutherford is credited with discovering the nucleus of the atom and giving us a big insight into what the structure of the atom is like. So our subatomic particles, the particles inside an atom, protons, neutrons, and electrons, we always use the lowercase symbols for them, for the letters P, N, and E. The charges, protons are positive, that's the PP rule, and then electrons are negative, and neutrons are neutral, have no overall charge. When we talk about the mass of a proton is 1 AMU. And AMU is a made-up unit to measure these subatomic particles. Instead of talking about such a super tiny amount of grams, it'd be like 10 to the negative 19th or something like that, grams. They made up a unit, and it's all related to the proton. 1 AMU is a proton. So a neutron is pretty much 1 AMU, and an electron is pretty much 0. You know, it's got a little bit of mass. It's just really, really, really small. It takes about 1,800 electrons to equal a proton, so about 0.006 AMU. So it's so small that we ignore it for the most part. Where we find them, protons and neutrons are found in the nucleus, in that very small, concentrated 99% of the mass of the atoms in that nucleus, and the electrons are going around. But when we think back at the neutron and its charge being neutral, well, to be neutral, you know, it's made of charged particles, so it must have an equal amount of positive and negative charge. And in essence, you think about a proton and an electron combining, and that would make a neutral charge overall. You think about the mass of a proton and electron combining. A proton is 1 AMU, an electron is pretty much nothing, just a tiny little bit. And so when you add those together, you pretty much have 1 AMU. So a neutron is pretty much a proton and electron combined. It's not quite that simple, but for right now, that's a great idea of how to think about it. So when we talked about the structure of the atom, there's some terms that we need to know. The first term is the atomic number. The atomic number is the number of protons. That's what it is. It's telling you hydrogen is 1, it's got 1 proton. Helium is 2, it's got 2 protons. Lithium is 3, it's got 3 protons, and so on, right? Now, the thing I expect you to know is also why. Why are these protons so important that they get to be the one in charge of what element it is, right? We could change the electrons and change the neutrons, it wouldn't change what element it is. But if you change the protons, you change what it is. Well, when we think about all these chemical interactions and what atoms are doing with their giving and taking or sharing of electrons, it all comes down to how well they hold on to those electrons. So the number of protons is what controls how well the electrons are bound to that atom. So that's why protons control what element it is. The atomic mass, like we said, electrons are pretty much 0, so we ignore their mass. So what's left to count up for mass? Protons and neutrons. There is the possibility, though, that we have the same number of protons, so it must be the same element, but they have a different number of neutrons, which doesn't change how it holds on to electrons or anything, but it does change the mass. So isotopes are the same element with a different mass. Or you could say they have the same number of protons, but a different number of neutrons. Now, the neutrons will help control how the nucleus is held together, because we got all these protons trying to repel from each other, and there is another force that holds them together, the strong nuclear force, but the neutrons help with that. And so by having an off number of neutrons it can make it unstable. So sometimes certain isotopes are radioactive, and other isotopes are stable. So it just kind of depends. The way we write the isotope symbol is we put the mass number up top, and then we have the atomic number down below, and then we use the symbol with it. So like carbon here, I'll use carbon, and all carbon has 6 protons, so we put atomic number 6. Most carbon has a mass of 12, so I would write the isotope symbol like this. Now, some carbon has, and this mass of 12 would be 6 protons, right, and 6 neutrons. No, the electrons don't add up for mass. Some carbon atoms have 6 protons, but they have 8 neutrons, and that gives them a mass of 14. So we write the isotope symbol like this, and we talk about carbon 12, or we talk about carbon 14. So that's how we identify these isotopes. And it turns out that carbon 14 does happen to be radioactive. Whoops. Now, atomic weight, if we take those atoms of carbon, we took a chunk of carbon and started counting up the atoms. We said, oh, well, here's a 12, here's a 12, here's a 12, here's a 12, here's a 12. Oh, there's a carbon 14, there's a 12, there's a 12, there's a 12, there's a 12. And we did an average. You do an average of all that, and it would turn out to be 12.011. Well, that is the number that we see on the periodic table under the symbol. So that is the atomic weight, which is the average mass of those common isotopes. So let's go back to Dalton's theory and talk about what things are not quite correct. So he said all matter is composed of extremely small particles called atoms which cannot be created, subdivided, or destroyed. Well, we know that's incorrect. Atoms can be subdivided. We could break up an atom. We can create atoms. Uranium is the largest naturally occurring element. It's atomic number 92. Everything after uranium, we would say transuranic elements, are all man-made. Plutonium, californium, einsteinium, americium, those are all put together by pushing other nuclei together and making a bigger nucleus. So, and we can destroy atoms too. We can break them up. We can annihilate them. E equals mc squared. We can turn them into pure energy. Great. So that part is incorrect. Atoms of a given element are identical in their physical and chemical properties. Well, it's partially correct. The chemical properties part is correct. They all react the same way, but their physical properties are not necessarily the same. We have isotopes. Different mass means that they have a different, that's a physical property, so their physical properties are not identical necessarily. Atoms of different elements differ in their physical and chemical properties. Yeah, that's pretty much true. Atoms of different elements combine in simple whole number ratios to form compounds. Yeah, that's true. H2O and CO2 and whatever else we got. In chemical reactions, atoms are combined, separated, or rearranged, but never created, destroyed, or changed. Now, this is still true because they're talking about chemical reactions. If we change the nucleus, that's a nuclear reaction, not a chemical reaction. Chemical reactions are all about electrons and giving, taking, or sharing of the electrons. So this should give you a good start on your homework. So now you can get to it and get busy, and we'll work on this more in class.